Okay, so yesterday on the front side of 5.1.1, we started learning some identities, right? Some of them should be coming familiar to you by now. And we're going to keep using these identities today. So you're probably going to be flipping your page back and forth. But yesterday was more, okay, here's some information, here's some other information, find something. It's like here's sine, here's tangent, find secant, those kind of things. Today, it's more about simplifying an expression. So if they give you some kind of crazy big expression, what can it simplify down into? What is, the nicer form of it? You'll notice up at the top of this page, there are 5 numbered pieces. I wouldn't say 5 steps, but there are 5 things to consider, or 5 ideas, when you're trying to simplify these expressions. So there are options that you could do. One option, if you have multiple fractions, you could get a common denominator to put them together as one fraction. Expressions are going to be easier to simplify if they're one fraction instead of multiple fractions. You can also reverse that. You can separate numerators by dividing each piece by the denominator. So if there's a direction we can go with it and we need to take a big fraction, separate it, that's an option too. Option 3 will sometimes be doing some factoring or foiling. Whether it be factoring things apart or whether it be foiling things together. So that would be an option to look for. Option number 4, looking for the Pythagorean identities. Remember we had that list of 3 Pythagorean identities. And those are probably some of our most important identities. But those Pythagorean identities, looking for those. Because if you see a Pythagorean identity, you might be able to replace it with something. And then the other option, if we were trying to figure out how to do things, take a problem and change all the trig functions so that they are all sine and cosine. Okay? You may not have thought about this, but every single trig function can be expressed in some combination of sine and cosine. Okay? Tangent, cotangent, secant, cosecant, they can all become some variation of sine and cosine. If you have everything in terms of sine and cosine, it might make the process easier. So these are the ideas we're going to use to simplify. We'll do several of them. We'll see how time goes and how we feel. But again, you're just going to have to practice on your own then. That's what it comes down to in this section. So as we look at example 1, the expression, or example A, sine cubed x plus sine x cosine squared x. Think about these 5 ideas, and if there is something that might get us started on example A. If you start going through that list of ideas, you can probably eliminate some of the ideas. Yeah, number 1, create common denominators to combine fractions. Are there even fractions here? No, so forget idea number 1. For the same reason, forget idea number 2, yes? And I would also say, could we forget idea number 5? Change everything to sine and cosine? It is all sine and cosine. Okay, so that takes me down to ideas 3 and 4. Factoring. You guys remember the idea of factoring out a GCF? If you're factoring out a GCF, it's in common in all terms, yes? So my first term is sine cubed, which means it has 3 sines in it. My next term is sine x cosine squared x, which means it has a sine and 2 cosines. So what do these 2 terms have in common? A sine x. So I'm going to take a sine x and write it out front. And if you want to write down what we're doing here, this is factoring out a GCF. Okay. If I take sine x and I factor it out of that first term, what is sine cubed x divided by sine x? sine squared x plus, if I have sine x cosine squared x, and I divide out a sine x, what remains? Cosine squared x. Are we okay with that step? Okay. Now, just taking one step doesn't mean you're done. Because in all honesty, is this any simpler? No, I haven't really made it any simpler yet. Okay, the other idea we hadn't used yet was idea 4, where it said look for the Pythagorean identities. This is where the more familiar you are with those Pythagorean identities, the better off you'll be. What was our top Pythagorean identity? Okay, so sine squared theta plus cosine squared theta equals 1. This says sine squared x plus cosine squared x. Does that matter? No. Whatever variable you have in there, it doesn't matter. Okay, it doesn't matter what you have in there. The idea that sine squared of something plus cosine squared of something means that this right here can be written into a 1. Now think about it. That whole parenthesis is now 1, because sine squared plus cosine squared equals 1. What did we already have out front? Sine x. What is sine x times 1? Sine x. It does. I agree. Is this simplified now? Is this a lot simpler than it was? Definitely a lot simpler than it was. I will say a challenge is knowing, have I gone far enough? However, when I get to something like sine x, I definitely, there's not really a question of have I gone far enough. We're there. And if you want to write it in, what was that step I used right here? I used a Pythagorean identity. Or if you ever see me write or say PI, Pythagorean identity. Okay? Write something down so you have the, so when you look at this later, you can figure out what we did to magically get to an answer of sine x. Okay. Ready to try B? As ready as it gets. Okay, so B. Secant x plus 1 times secant x minus 1 over sine squared x. Start looking through your list of ideas and seeing what options might be able to help us. I would not right now. Yeah, okay, so what about changing everything? She was asking, what about changing secant to cosine so we're all in terms of secant and cosine? I would not at this exact point. That might be an idea later. I don't remember exactly how this problem goes. Only because then I'm going to have fractions within fractions, and I'm not looking for that. Yeah. When I see those two parentheses on top, my brain's saying FOIL. Okay? When I see those two parentheses on top, my brain is saying FOIL. So that is our starting place. So, secant x times secant x. Secant squared x. Secant x times minus 1. Minus secant x. Secant x times positive 1. Plus secant x. Because what's going to happen here? They're going to cancel because what are these called? Do you remember the vocabulary? Conjugates, yep. When the pieces are the same, the middle sign's what's different. These are conjugates. So when you multiply conjugates, it's designed so the middle terms cancel out, right? That's good. We like that. And then last, 1 times negative 1. Minus 1. So my numerator just became secant squared minus 1. My denominator, is still going to stay sine squared x. Thoughts on my next step? My Okay, well, I do want to talk Pythagorean identity, although I was actually wanting to talk Pythagorean identity for the numerator. And here's what I'll say. If you have something like, just the sine squared, yeah, we can manipulate these Pythagorean identities. The form they're given in doesn't have to be the only form of it. That secant squared minus 1 on top, what Pythagorean identity does that remind you of? Or is it pieces of or similar to? Okay, that middle one, I'm going to write it up here, of 1 plus tangent squared theta equals secant squared theta. How does that relate? Yeah, if I manipulate this, take this positive 1, subtract 1 over, then notice what happens. We have tangent squared theta equals secant squared theta minus 1. So what do you know? A secant squared theta minus 1 can be replaced with a tangent squared theta. Or in our case, a secant squared x minus 1 can be replaced with a tangent squared x. Okay? The Pythagorean identities, we have to manipulate them at times to make them work and do what we need them to do. Here's my things. When I see something, a term squared, so some trig function squared, and there's a plus or minus 1 involved, that's where I often start examining my Pythagorean identities and seeing if they will help. They won't always help. Sometimes we can't get the signs to work out. But if they can, by all means, let's do it. So, secant squared x minus 1, I'm going to replace with tangent squared x. And we're still over sine squared x. How did I get from that step to the next step? That was a Pythagorean identity. Technically, we can't. And my reasoning we can't square root both of them is it's not an equation. If I'm going to do something like square root them, I need to be able to square root both the left and the right side of the equation, but this is just an expression. So we have to leave the squareds in there. We need to go a little bit farther with this. There's a little bit more simplifying we can do. We foiled. We had a Pythagorean identity. Other steps up top you see that might help? Vincent?
We can use the first quotient identity in order to find cosine of theta.
Okay. So talking about the fact that what do we know about tangent? Tangent, is this what you were meaning?
Yeah.
Tangent is sine over cosine, yes? Now, good to know. That means tangent squared is sine squared over cosine squared. So that still applies. When we have that sine squared over cosine squared and then we're dividing by sine squared, this is going to clean up quite a bit. Okay? Now, you can go ahead and use your quotient and have a fraction within a fraction. Or, let me write this out sideways. I think some of you will like it a little bit better. So if I change this and write it out horizontally, so it says tan squared x divided by sine squared x. I didn't change anything technically right there, yes? I'm just writing it out so we can see it a little bit better. Instead of vertical division, I made it horizontal division. What do we know about tangent? Our quotient identity says that tangent is sine over cosine. So that means that tangent squared is sine squared over cosine squared. How do I divide by sine squared when we're talking fractions? Yeah, so dividing by sine squared, it's like sine squared over 1, is timesing by...
Here's time interruption. Anyone going on the art film trip needs to report to the cafeteria doors quickly. Thank you.
Okay, so dividing by sine squared is multiplying by the reciprocal, 1 over sine squared. And basic math skills here. What happens? Sine squareds cancel. And then before I go any farther, do you guys need me to write it in? How did we get from tangent to sine over cosine? We used our quotient identity. Write in any steps you need that might help right now. So now when our sine squareds cancel, I am left with one over cosine squared x. One more step.
You put a big old circle around it and you leave.
We're going to circle our next answer.
So 2 steps. 3 if you count the walking out the door.
1 over cosine squared. What do you know about 1 over cosine? Equals something. Cosine is the reciprocal of secant. Cosine is the reciprocal of secant. So if 1 over cosine equals secant, then 1 over cosine squared equals secant squared. We almost could have stopped at the previous one, but if you can get it out of a fraction form into just a basic trig function, that's going to be better off. Okay. So you're starting to see why I say it's going to take practice to get these figured out, isn't it? It's going to take practice, of you working through these problems to see what you can do. I'll tell you up front. Monday, my plan is to go over some questions on these odds as you attempt them. Okay, so I want you attempting the odds for Monday, but then my plan will be to go over some questions and help you find some ways to do the ones you get stuck on. Okay? I don't know. I will not probably, I probably will not bother walking around at the beginning of class Monday to check it. However, the one thing I would do is make sure you've at least started it and gone through it and tried things and didn't just, okay, I got to number 11 and I'm done. Like, that's not giving a full-hearted attempt, Especially because number 11 is still probably stuff we did yesterday. Again, I'm going to keep showing you examples. You've just got to work at them, okay? Questions on that last one that I did? Is there anything I need to clear up? It's kind of preparing you for other things. Like if you're trying to solve equations, which solving equations is the next part of lesson 5.1. It would be you'd be doing something with mathematics here. Okay. Or, trig functions do have some applications if you think about it. Again, it has to do with things, things within mathematics of trying to simplify and get you, if we're giving a big thing, we can't really work with it, but if we can simplify it down, we might be able to work and do something with it.
I'm guessing it has something to do with triangles in real life.
There you go. Yeah. Just be, all the trig, it relates to those right triangles that, So there are, don't walk out of here thinking, oh, I'll never use trig. It depends. What are you going into? Some of you will not use trig after high school. Some of you, it will end up showing up in what you do. It just kind of depends, right? So, okay, let's try C. It does not. Okay, but that's a good point for me to show or to share because that's a really common mistake. So C, cosine x over 1 minus sine x over cosine x. So the first attempted observation up here, so common and it's so easy, is, is that a Pythagorean identity? Why is 1 minus sine x not part of a Pythagorean identity? Why do I have to veto going the direction of it's not squared? Okay, so when we talk Pythagorean identities, there have to be squares on those trig functions. Okay, so let's get that mistake out of the system today. Because it happens. Trust me, it happens a lot. So we cannot talk Pythagorean identity at this point. Am I saying we won't talk Pythagorean identity later in this problem? No, Pythagorean identities appear a lot. Okay. I see two fractions. Number 1 says get a common denominator. So we're going to work to get a common denominator. Okay, another common mistake. Cosine x's cannot cross cancel because these fractions are not multiplying. If my fractions were multiplying, I'd be right there with you. Let's cross cancel. Oh man, I've got rid of that Pythagorean identity. It's getting a lot easier here. Unfortunately, no. When you're add and subtract, you can't cross cancel. Not to get your correctness points, right? Okay, so what is the common denominator? One denominator is 1 minus sine x. The other denominator is cosine x. Do they have anything in common? Yeah, x doesn't really count. So do they have anything in common? Not really. So if your two denominators do not have anything in common, how do you get the common denominator? You multiply them together, right? Kind of like if you're adding, say, 1/2 and 1/5. I'm trying to get something that, if we add 1/2 and 1/5, do 2 and 5 have anything in common? No. So how do you get your common denominator? It's 2 times 5, which is 10, yes? Now, what do you do to this denominator to get to that common denominator? This one you'll multiply by 5. What you do to the bottom, you do to the top. Over here, what do you do to the 5? Multiply by 2. Okay, you see where, that's basic math, right? That's our basic fractions we're supposed to know how to do. So, my common denominator is going to be 1 minus sine x times cosine x. That's going to be my common denominator. What do I have to do to that first fraction? What is it missing in the denominator? Okay, it has 1 minus sine x. It's missing a cosine x. So I'm multiplying by cosine x. What I do to the denominator, we do to the numerator. So my denominator, cosine times 1 minus sine, is what I already have written down, yes? On top, what's cosine times cosine? thought he was going to say it. Cosine squared x. Cosine times cosine. Cosine squared. He got scared and backed off. Okay. What type of problem is this? This is a subtraction problem, yes? Because I'm going to go ahead and put it together all in one fraction. What's my second denominator missing? It has the cosine. What's it missing? That factor of 1 minus sine. If I multiply the denominator by 1 minus sine, got to multiply that numerator by 1 minus sine. Now, you have an option here. I'm going to, I say, do you want me to distribute as is, or do you want me to wait a step? I mean, my options are, I can just write it down as sine x times 1 minus sine x for the moment. And I guess I'll do that for the moment. If you want to go ahead and distribute, do it. That is fine with me. So now, because what am I doing in this step now? Not yet. I'm distributing right now. So I have cosine squared. I'm distributing this sine x. Minus sine x times 1 is minus sine x. Minus sine x times minus sine x. Plus sine squared x. Now, in the denominator, sometimes we want to put these together. Sometimes we don't. And it's really one of those things you can't really tell until something gives you that direction. I tend to leave them apart until I hit a point where I feel like I need to put them together. Because more often than not, you end up wanting them apart. So I'm going to do 1 minus sine x times cosine x. Okay? We've got to do some work with that numerator.
No, because of 1 square.
We are reviewing all these lovely algebra and fraction rules that you have long since forgotten, right? Okay, so, yep. Look at the first piece in the numerator and the last piece in the numerator. What do you notice about that first piece of the numerator and that last piece of the numerator? It's a cosine squared x, ignore the middle, plus sine squared x. Cosine squared x plus sine squared x is equal to 1. Now, if you want the visual, and I'm going to do it for the sake of the notes, you can just go ahead and take those both out and put in a 1. What I'm going to do is just reorder it before I do that. So cosine squared x plus sine squared x minus sine x. And the point of that is that cosine squared x plus sine squared x is going to be replaced with a 1 because of Pythagorean identity. So right there, can I write PI and you guys are getting the idea at this point? PI stands for Pythagorean identity in my book. I put P dot I, so cosine squared plus sine squared x is 1 minus sine x over 1 minus sine x times cosine x. Okay, so when we're canceling within a fraction, we can cancel like factors. One of my factors in the numerator is 1 minus sine x, or excuse me, one of my factors in the denominator is 1 minus sine x. The only thing in the numerator is 1 minus sine x. So because that's the only thing in the numerator, that makes it the only factor, and it's one of the factors in the denominator, yes, you can cancel those. What does that leave in my numerator? 1. What is left in my denominator? I have 1 over cosine x. But we know better than to stop there. We're going to write one last answer. 1 over cosine x is the reciprocal of secant x. So 1 over cosine is secant. Three different problems. We've done 3 different varieties here. Okay? Everything has different steps. You've noticed we factored, we FOILed, we've used Pythagorean identity in all of them. We had to get a common denominator, we used our quotient identity, we've talked, I guess I didn't mention at the end, officially these at the end would be reciprocal identities, right? I didn't mention that, but if you want to think about that is the reciprocal identity that happened there. Well, keep in mind, this is one thing. We're going to spend quite a bit of time working on it, but come test time, this is one thing in a whole chapter. So it's not like you're going to have tons of these.
There's no other way out. We're just.
Okay. I want to look at E on the bottom. I would say that E is the easiest problem on this page. Okay, so first of all, that D should be F for the next problem. Like the problem ends there. Okay, that's just a whole other problem. Okay, so problem E. The tangent of negative x times the cosine of negative x times the sine of negative x times the secant of pi over 2 minus x. I have red flags going off all over in my head because there are 2 types of identities we have to look at here. Okay. When I see a negative variable inside the parentheses, that tells me we're going to look at our even and odd identities. Okay? What about when you see that pi over 2 minus x in parentheses? That tells me I'm going to look at my cofunction identities. Okay? These to me are some of the easiest to identify because, oh, negative x, okay, I got to go for even odd. Oh, pi over 2 minus x, I got to go for the cofunction. So use your identities and replace each of those. According to our even and odd, what does tangent of negative x equivalent to? Okay. Negative tangent of x. Okay. Times. According to our even and odds, what does cosine of negative x equivalent to? Positive cosine of x. Times. What does sine of negative x equivalent to? Okay, that's negative sine of x. And according to our cofunctions, what does secant of pi over 2 minus x equivalent to? Cosecant of x. So first of all, I got rid of all those negative variables within my trig functions. Got rid of that pi over 2 minus x. You guys have thoughts on where to go next? Okay.
Make everything.
Okay, so changing cosecant to sine in terms of sine is going to help. While we're there, there's our other sine, there's a cosine. What do we know about tangent? It can be changed too, can't it? So let's go with the idea of make everybody sine and cosine. Now, I'm guessing the whole idea of cosecant is you see what's going to cancel after we turn cosecant into sine. Okay, because of the reciprocal there. But let's change everybody to sine and cosine. So, what is negative tangent when I change it to sine and cosine? Still negative. What's tangent? Sine x over cosine x. While I'm here, what's cosine as a fraction? How do I write it in fraction form? Still cosine, but in fraction form, it's what? Cosine over 1. I'm just trying to set us up for the final step here. Negative sine x. It's already sine, yes? How do I write that as a fraction? Negative sine x over 1. What do we know about cosecant? It's 1 over sine x. Okay, guys. Finish it off. We're there.
Cancel.
Yes. Now you get to cancel because it's all multiplying to fractions. Yep. Okay, so we can cancel what? Cosine cancels with cosine. Sine cancels with a sine. A negative times a negative makes a positive. What remains? Sine x. I know you guys, I don't know, maybe you guys don't see it. I think of that as one of the easiest problems we've probably done today. I know at this point you guys are just over it. I get it, okay? But again, I like it because I see the negative x's. I see the pi over 2 minus x, and I know what to change to. After that, it was just changing everybody to sine and cosine. Okay, I'm going to stop there. No way we're getting through anything else here. So, your job before Monday is to work your way through and attempt these odds, okay? The first part goes back to what we were doing yesterday, okay? So, you need to look back at yesterday's notes. The second part goes along with this stuff here. Do not stop partway and say, I just can't do it. Just because maybe you hit a couple, you're like, I don't know where to begin. Keep trying them. Because just because you can't do 29 doesn't mean you can't do 31. They're not all the same. Okay, so